special values. We talked recently about converting degrees to radian measures, just a way for us to different units for measuring rotation. And we learned that that calculation of converting between the units was pi divided by 180 to go from degrees to radians, and multiplying by 180 over pi to go back to degrees again. And here are a collection of common angle measures, and in particular the ones that we're going to need to know really well for the sake of trigonometry. We'll talk a little bit more about this in the future, but what we've got here is the unit circle going around from standard position on the positive x-axis, and the degree measures and their corresponding radian measure of rotation as we go around to 360 degrees back to 0 again. What we've got here on the outside of the unit circle are coordinates. These coordinates are given to us by our old friend, the trigonometry functions, the x-axis corresponding to the cosine of an angle, and the y-axis corresponding to the sine of an angle. Just remember that these trig functions relate an angle measure to the ratio of the sides in a triangle. The sine function being the opposite side from the angle, which would measure the position of the y-axis of some point P that was on the unit circle, and the cosine being the adjacent side to the angle, so the x-axis position. So we could kind of correspond cosine and sine to the x and y coordinates of a point. The particular ones that we're going to be interested in, and the ones that we'll have to commit to memory, are these special right triangles that we've looked at in the past with degree measure. On the right-hand side, we have the 30, 60, 90 right triangle, here given to us with its radian measure of angles. Pi over 6 corresponding to 30 degrees of rotation, pi over 3 corresponding to 60 degrees. And here are the ratios of the sides of a triangle with a hypotenuse of 1, which would be the radius of a unit circle. And on the left-hand side, the 45, 45, 90 right triangle, again with a hypotenuse of 1, will always have these measures for its other sides. You can confirm that for yourself using the Pythagorean theorem if you're in doubt. This chart is essentially what we're going to need to know really well in order to be effective in the future as you go through trigonometry. Essentially, for each measure of rotation in degrees, you should be comfortable with the next row, which is the amount of rotation in radians, and beneath that, the output of the sine function for that angle measure. Whether it's degrees or radians, you just have to let the sine function know what you're putting in, and your calculator will spit out the correct value. So you always need to know the mode of your calculator when you're doing these. But these particular outputs you're going to want to have committed to memory, and they come from these special right triangles. So the sine of pi over 6 is going to be a half, that's the opposite side. The sine of pi over 4 is going to be the square root of 2 over 2. So this chart simply gives us what those outputs of the trig functions are going to be, and those outputs of these trig functions are simply the length of the sides of a triangle. This is where we need to start connecting all of these ideas. Let's actually jump over to this screen for a moment. Again, I'll share all this stuff with you. These Desmos activities connect the angle measure and the trig functions to the points along a circle. And here, hopefully, you'll begin to see all of these connections between the various concepts in trigonometry. As I adjust the slider for the angle measure, we'll see our radius of the circle, or our hypotenuse of the triangle, beginning to rotate along the outside of the unit circle. And when I get to 30 degrees, I sort of land on this special point over here. And we can see that it's being approximated to 0.866, 0.5. This 30 degrees of rotation, or pi over 6 radians, shows us this special reference triangle, essentially one of the triangles whose values we need to know well, these special values of exact values. So instead of having the calculator give you 0.866 when you ask about the cosine of 30 degrees, or pi over 6 radians, which also corresponds to the x position of this coordinate, you need to be aware that the cosine of 30 degrees is the square root of 3 over 2. That is the precise, irrational, exact value of that trig function. If you write 0.866, that's good enough as an approximation, but it is not sufficient when we're doing precise mathematical calculations. Also corresponding to this exact same 30, 60, 90 triangle, the sine of 30 degrees is 1/2, exactly 1/2. This 0.5 decimal value here is exact in this particular case. As we continue rotating around the circle, we hit the next point, which is what's reached when we've rotated 45 degrees, or pi over 4 radians. And we can see here again these decimal approximations of the outputs, which give us the x and y coordinate, or the cosine and sine of the amount of rotation around the unit circle. And we've got another reference triangle there, the 45, 45, 90 triangle, which, again, with a hypotenuse of 1, which is the radius of the unit circle, and the x and y value of the sides of that triangle, which, again, with precision, square root of 2 over 2 for both the x and y, or both the sine and cosine of 45 degrees. These approximations are not exact. So we get one more as we rotate around, and we hit 60 degrees. Essentially what we have here, though, is a triangle that's exactly, actually get to 60 degrees, exactly the same or congruent to our 30-degree triangle. It's just in a different configuration. Now my 30-degree angle is up here, and my 60-degree angle is here at the origin, or the central angle of the circle. All this terminology you want to begin tying together. In order to truly understand this well, you want to connect all of these ideas. And what we get is essentially a swap between the x and the y values of this point and the cosine and sine of the angle measure. We're in the same triangle, essentially. So we can look at it here. We're in this 30, 60, 90 triangle. We're just looking from a different perspective. If I look at the 60-degree angle, the opposite side is the square root of 3 over 2. If I look at the pi over 6 angle, the opposite side is 1/2. So the sine and cosine within these triangles are just observing different sides as opposite or adjacent. We see them as two different triangles in our unit circle, the 30-degree central angle or the 60-degree central angle. But the values of that triangle, its shape, it's congruent. So sides of 1, 1/2, and square root of 3 over 2 exist in both of these, the green and the purple triangles. Those are essentially our reference triangles within the unit circle. And those same triangles just repeat themselves as we go around into the second quadrant. This is where things get a little bit weird, but I'm going to sort of go past the 90-degree angle, which gives us another special value at 0, 1, and follow along, continuing to rotate around to a measure of 120 degrees. From here, I'm not going to draw the triangle back into the first quadrant. I'm going to drop that perpendicular down into the second quadrant, to the x-axis. So what I'm seeing here is a mirror image of the purple triangle in the second quadrant. And if you think about the amount of rotation, I've gone 120 degrees, so it means another 60 degrees would take me to the x-axis to complete this 180 degree or pi radians of rotation. So essentially this purple triangle here is congruent to the one in the first quadrant. But something changes, and the reason why we have a different triangle is because our output of the cosine of 120 gives us a negative value, because in the second quadrant, this x position is negative 1/2. The sine of 120 is still the same, square root of 3 over 2, but I've moved across into the second quadrant where the sine or the y values are still positive. So a lot of things should be coming together and being connected. One, that the triangle that gets formed by this particular configuration of 120 degrees is congruent to the one in the first quadrant, exact same dimensions, but the place that the position of the hypotenuse, it's pointing now to negative on the x-axis. That particular point has a different value. And this trend continues. As I go down around to 135 degrees, the triangle that I would drop is congruent to the one in the first quadrant. The values simply change. So while it appears like you have to memorize 12 different positions and points, we're just getting these mirror images across the x-axis. The only thing that's changing effectively here is the positive and negative, or the signs of the x and y values. And again, these x and y values corresponding to the cosine and sine of the angles as we rotate around the unit circle. So these positions, these points along the unit circles are the ones that you're going to want to have committed to memory. You're going to want to sort of call up a vision of this particular unit circle. So these are the critical exact values that you want to be able to construct. And you should be able to eventually draw this unit circle with a fair amount of accuracy, being aware of the degrees of rotation from standard position along the x-axis, the corresponding radian measure for those degrees, and the x and y value of the point that lies on the unit circle. And understand that that point along the unit circle is giving you the output of the sine and cosine of the angle. We're connecting rotation with x and y position as we go around the unit circle. This fundamental concept is essential to being effective when you're working with trigonometry. It's the essential idea that ties a lot of this all together. So we're getting this sort of roundabout picture of all these different elements, and you're going to want to connect them all and be able to sort of see the overlap between these ideas.